Raise your hands if you are like in the data engineering space. Yeah? Raise your hands if you are in the data science AI space. What are the rest of you doing? Like, can somebody say what they do really quickly? Yes. You work in finance. What are you doing here?
We research on publicly traded companies.
Okay.
Software, so I'm just here learning about the space.
Okay, awesome. Who here is learning about the space? So a little bit about me. I'm a product manager at a company called Datastrato. We are an open source data catalog, which we will be talking about today, don't worry. If you don't know why I'm so excited about that, it's because this has been a few weeks worth of a lot of open source catalogs. So we're gonna get to chat about that. And I also am a Google Women Tech Makers Ambassador, Continuous Delivery Foundation Ambassador. I organize a group here called the Data Engineer Things Bay Area chapter. I'm also part of the Linux Foundation AI and Data and Gen AI Commons. So just like I kind of, I get around. So basically, a lot of what I really like to do is to figure out what the intersection is between DevOps/data ops, data engineering, and data science/machine learning. Because I think in any organization that wants to be functional and deploy machine learning applications, these three teams need to be able to talk, right? And we're going to learn why, maybe, spoiler alert, that's metadata. So to kind of get started, I want to go over some background stuff in terms of why this is so important for us to figure out, how can we make these sort of things and disciplines interoperable. So first I want to start off with data architecture. So we've gone from really structured, highly controlled architectures that have really kept a very strict format and then evolved into looser, unstructured formats. And then kind of figured out, hey, you know what, this isn't really working for us at scale. Things are kind of a mess. We can't govern this very well in terms of training our models. Like we don't really know what's going in and what's going out. And so essentially, if we look at the data lakehouse and the data mesh formats, we see that we've kind of gone into this hybrid semi-structured space where we have structure at this higher level in terms of a lakehouse and in terms of, say, data products, but we're still trying to keep this sort of flexibility to maintain what we consider high velocity flow or streaming data as well. And so essentially we now have to have infrastructures that are able to manage structured and semi-structured data all in the same vein. On top of this, if you go one level even higher, each cloud ecosystem has their own sort of set of tools and formats that they like to use. And so these aren't always interoperable with each other, which make it very complicated. So for instance, can everybody hear me okay? Yeah? Okay. I just wanted to double check. Instance, we have different public clouds that people can use. We have private clouds, cloud native formats. And so with all of these different tools and ecosystems, there's a lot of complexity, especially when you're dealing with companies that, say, are doing a multi-cloud architecture. And so essentially, we've kind of noticed that over the years, things have moved from on-prem, where things were really structured and easy to kind of manage, to then eventually cloud and serverless, and now to multi-cloud. And we're noticing these sort of open formats that have come across, interoperability being a huge theme. And this is kind of where a lot of these catalogs have, in these past couple of weeks, have maintained a lot of their focus. On the parallel side, so we talked about data infrastructure a lot, machine learning in itself has also gotten very complicated. We are no longer just using clustering and simple machine learning methods, although sometimes we really should just use linear regression. But instead, we now have methods like RAG pipelines. We're merging models where we're piping the outputs of different models into each other and using them as inputs. We're doing methods like fusion. And so to actually keep track of what's going into these models and how we're actually managing them, the artifacts that are around that, it becomes quite complicated. And in turn, for those on the R&D side, I think we kind of noticed that actual RAG as we know it here and now, and from what we see in demos, is quite limited. And so it assumes that all of the data is in a single store, it's in a format that's easy to plug into the pipeline, and it's sort of standardized, and we don't really have to worry about the version control. But in production, it's not necessarily going to scale extremely well. So if this is a pretty straightforward RAG pipeline that we see here, where we have our vector store and the documents that we're feeding into. And so essentially, this looks great in theory, but at scale, and if we introduce personalization into this, it becomes quite complicated. And one thing I also want to mention too is that all of the stuff that I mentioned before in terms of infrastructure, that kind of all happens in that tiny one circle that says load documents, because it's so easy to just load documents into your RAG pipeline and then assume that the rest of the pipeline is going to work. But that's actually oftentimes 90% of the work is getting your data stores into a place where you can actually then feed it into a machine learning pipeline. So again, knowledge management is quite difficult when you're working with this at scale and you're working with like billions and billions of documents. It's hard for you to understand as documents are changing and being edited constantly, you know, what the velocity is and how much is going in and what the distribution of that looks like, what the lineage of those documents are and how you're tracing them to their source systems, and what the life cycle of those documents look like. And so, you know, my kind of thinking along this line is, as we think of data products with the rise of data mesh, we also want to consider RAG as a product as well. How are we serving RAG within our organizations to other teams, and how are we making it reproducible? And in turn, RAG has also become very complicated. So if you don't know RAG, like retrieval augmented generation, like we have gone a far way from really just like kind of optimizing chunk sizes and being able to retrieve certain pieces of documents to now doing things like advanced retrieval with the rise of vector stores and, you know, post-RAG methods and pre-RAG methods. There's a lot of different ways algorithmically. It's not really the focus of this talk, but there's a lot of things that we can do within RAG itself to optimize. And with that, we need data infrastructure that actually supports that. So an example could be agentic behavior, where you have, say, a data agent that then does some sort of function on the customer's behalf and actually does some sort of query planning. There's also other sorts of retrieval where you're having different queries that are then being joined together to provide more context-rich answers. And of course, fine-tuning, which was kind of the original approach of how we fine-tune or how we increase the performance of a lot of machine learning systems. So in turn, we've had these sort of things like vector search RAG, which is using a vector database to optimize your chunk size and to do your embeddings. And it's very straightforward, and most people who do RAG end up doing some sort of vector RAG as well. And now we've also noticed that because the answers are not as rich as we want, we're utilizing knowledge graph RAG as well. So this is when you can do a hybrid approach where you have vector search and knowledge graph. But knowledge graph is really like in your entire data infrastructure, you implement one giant knowledge graph that then has the semantic similarity search that you want, and not just sort of like in terms of chunk size. And then you supplement your original answer with the knowledge that the semantics gives you. And this can actually be quite complicated in terms of the queries that you do against knowledge graph RAGs. However, because of that, it's more knowledgeable, but it's also much slower. So it's not the most scalable solution. And now we're kind of entering into this new age of what could possibly be catalog RAG as well. So this is when you have like a data catalog that sits on top of your entire architecture, and then you use agents against that. And, you know, in sort of an embedded way to provide not only governance features, but to provide other sort of functions on the user's behalf. And of course, this is a little bit less heavy in terms of migrating your entire architecture, because to implement a knowledge graph against all of your data is quite difficult. And in terms of vector databases, they're pretty easy to implement. However, you have to do it on the actual RAG pipeline side. And so you're not really doing that much on the data infrastructure side. But you kind of need both, because vector databases are quite hard to, you know, admin as well and to govern. And I think that's kind of where we're trying to find these hybrid approaches that can give us something that's context rich while still providing the performance that we want. And so, yeah, hopefully that was a mouthful, and I know that that was a lot. I'm happy to talk about it more, but this is a very high-level overview of so much. And essentially, the TLDR is that, you know, on the R&D side, we've focused so much on creating the best models, on creating the best machine learning pipelines, but we haven't really thought about how we're actually, you know, changing our data infrastructure and enabling our data infrastructure to help these systems perform a lot better. And we're entering that stage now, but we're still very focused on performance, right? And performance is great, but it also becomes very costly. So a lot of organizations I talk to, for instance, think that maybe they can just throw a giant graph database on top of everything, which sounds like a bit of a nightmare to maintain, but if it works, it's amazing. But maybe it might not be something that works very well moving into the future, because as you saw before, architectures change over time, and there's a lot of different formats out there. There's a lot of different stores. Things kind of have to live in this multi-cloud era now. So challenges in RAG development. So first, obviously I kind of mentioned this before, that the more complex the queries are, the more rich you want your responses to be from your LLM, the slower it's going to be. And so you have to kind of tweak around that as well in terms of like how performant you want it to be and how much information you want to feed into it. As well, how you're going to synthesize new information. This is really important as you have streaming data and as you're trying to make things as real time as possible. And so, this kind of becomes a really huge hurdle. And with that gets tied into latency and performance optimization. And on top of that, and we're kind of just catching up to this now, is all of this kind of needs to happen in a way that's like legally compliant. We can't just like throw all the information in and make the best amazing, like, the best application, but without thinking about the user's data. And so how are we actually governing that data as well? And of course, we want it to be flexible enough to change with our architecture and new data stores. Around that, though, as we're deploying machine learning models, so this is a really great paper by Google. It's called The Hidden Technical Debt in Machine Learning Systems. And so even outside of your machine learning pipelines, there is so much code around just serving an application or an LLM product where you have to consider the technical debt that you're incurring when you're trying to build AI within your organization. So a really great example is, of course, how are you storing the features? How are you managing them? How are you governing all of the aspects around this? How are you doing data observability and quality? Because your data quality will affect your end results so much. How are you actually, tracing your cloud resources and, your resource management around that? And there's a ton. And once it's out there in the wild, you need to monitor the performance of these things as well, right? So, of course, the different components of a machine learning platform that come in are, of course, you want to have supported polyglot data storage. You want to ensure that there is some sort of data pre-processing, which has to happen. You're converting distributed data stores into data frames, for instance, and your feature engineering that go around that. You want to be able to develop your models and have that source code available. You want to manage those models because you're oftentimes developing so many models at once to bake against each other, and you want to be able to version control those. And then you want to deploy and serve the model. So, we talked about RAG for like 20 minutes, but there's so much even just around RAG, and there was so much that came before RAG that we talked about. And so this is like a really big end-to-end view, and that's why I was scared about finishing my talk on time. This is a 2024 screenshot, and it's not even the code page of the current ML, AI, and data landscape. There's so much that's part of this, and new tools are getting added every single day. And yeah, I could not even see it on my laptop. It's crazy. And you can even see, like, there's more here. Like, this is cut off. This is just what I could screenshot, which is insane. And even within the MLOps tools landscape, so this is kind of a select few that I got from MorangoDB, but there's a ton around this, and even just within the last 2 weeks with all these conferences, more and more have been announced. And so tools can kind of come and go that try and address different parts of everything that I just said, and I just said a lot. How can we kind of create a language around all of these that allow people to use the tools that they like and allow the best tool to come forward without making migration a huge issue, right? In turn, because people love their tools so much, depending on the team that you're working with in an organization, you're going to have different silos. So a data infrastructure team will have a very specific stack and a very specific language that you use, usually Java, that they really like. And then in turn, you have the higher level architectural complexities that go on, and the way that these teams operate are actually quite different between your data infrastructure team, your data ops or DevOps team, and your machine learning team as well. And so you have these silos that happen at 3 different levels. And so like everything that I just said, it's like this very quick high-level overview, but really like whose job is it to kind of make sure all of that works together? It's quite rare. And so what you see in practice is that nobody knows anything about what the other team is doing and what's actually happening in other parts of the stack. And this becomes really difficult because you have these performance bleeds everywhere, you're bleeding money, nobody knows how to optimize everything, but everything that I just said has to kind of work in concert together. So there's a lot of incentives to solve these sort of siloed issues. Of course, you want to streamline processes as much as possible and ensure interoperability between all of your tools and formats. Of course, consistency of all your data is a must. You need to be able to trust your data in order to trust your results. Eventually, organizations are going to have to worry more about AI governance and the data management that kind of comes around that. And essentially, we do want to move towards unified architectures and data. And what does that look like? Well, we're kind of seeing the peak of that now. And so, having end-to-end visibility is also extremely important. How are you managing things from source to consumer? And how are you going to optimize across that entire pipeline? These silos and all of these different components that kind of move against each other sometimes as teams get settled in become a huge disadvantage when like a C-suite or a VP level decides, okay, we're going to do AI now. Well, does our data architecture support that? Or do we have the right processes in place? Like, what are we even doing? How can we even implement it? And so it's extremely important for us to create a unified layer in which everything can speak to each other. For us, that's metadata, and that's kind of the whole point of this talk, right? How can we create a layer in which all these different tools that all these different teams are working on can peek into each other, but can also have controlled access across each other, and then feed into something like, say, like a machine learning pipeline, and then be able to be trusted and then managed effectively. So I'm going to switch over a little bit to talking about metadata, which is essentially what this talk is supposed to be about, but I wanted to set the scene. So I talked a little bit about before how we had traditional data warehouses that had highly structured data. And essentially, I think this worked really well when we had traditional data catalogs and data dictionaries, where we just kind of described the data in terms of a business glossary and those use cases, and it was very complementary to each other. But now data has such a high velocity in terms of event processing, unstructured data, the actual version control of that data, and the non, like, I guess, warehousey format of it, and all the different sources that we see. And so we're noticing a lot of active metadata now that's become more granular in terms of its format, but also its description. And so there's a really cool book called Event-Driven Data Mesh. Would highly recommend it, but I won't be going into it too much. So in turn, what we've seen with metadata is that instead of being used and being there for certain teams for a very specific purpose, it then became this common layer for people to kind of pull off of. But now, because metadata can be so rich and descriptive in terms of what it is, it can now be the basis in which you push and pull all of your different processes and tools off of. And that makes it really exciting because it can be this wrapper around your entire stack that all of these different tools and apps can use. And having active metadata like that acts as a trigger for something or acts as a receiver for something can be really exciting. So for instance, a data engineer might use metadata in very specific ways. And I won't go through all of this, but essentially the idea is to govern and to make it reproducible, right? You want to ensure that your quality and observability is there. You want to be able to do things like metadata search. You want to be able to trace your data lineage. This is extremely important and a very traditional use of metadata for a data engineer. A machine learning engineer, in turn, might use it as sort of this way to package machine learning code. So they might use it to, be able to search for relevant entities and be able to tag them, to understand the performance differences between different models and features, and to reuse different artifacts so that you're not bleeding all of these resources and training new models or to kind of tweaking the models that already exist. And you want to be able to capture all the related settings. So it's sort of like a scientist experiment. You want to reproduce all of your different, I guess, like things that you've got going on so that you can make it reproducible. But this is sort of still in the very experimental phase. When it goes into production, it becomes almost the same as this in a lot of ways. So this might be like a schema design of what you might see metadata actually look like. And so you can see that there's a lot of data that's not even related to the actual data that's kind of being put in, but it tells us so much in terms of context of what went into this and how we're scoring it and what the life cycle is and how we evaluate it. And this becomes very rich and important for other applications to be able to pull off of. So in terms of metadata, I think that it's pretty safe to say that a lot of big cloud solutions actually use metadata very richly internally. So say if we looked at Microsoft OneLake or we looked at GCP, the way that they get their tool ecosystems to work so well together is through using metadata to feed into each other. But a lot of that actually isn't exposed to the user. Now we also have the open source Databricks Unity catalog, but you can see that there's a difference between the open source Unity catalog and the closed source Unity catalog, and it's, again, very preferential to their tools that they have in-house. And so they are able to ensure a ton of interoperability and this really rich ecosystem, but you kind of are still stuck in this one specific cloud, which makes it really difficult. And so there's also the case of FinOps as well. If you want to be able to do this and leverage it in a really good way, there's a lot of really great financial incentives to do so. But our incentive here is to figure out how can we recreate what a lot of these big guys have done, but in a truly open way so that you can plug in any tool that you want, any format that you want, any sort of pipeline that you want. And so this is kind of the conclusion that we've reached, which is a unified metadata catalog. And so essentially, if you have all of your metadata being pooled into one spot and managed and following like a very similar format to each other, can you use that as the common layer for all of the other tools to pull out of and into, and then not have to worry about what's actually under the hood or where it's going to be pushed into? And so this is kind of our idea in thinking, is that if we allow people to be flexible with their architectures and we allow people to do what they want to, but create a backbone that provides what a safety net for them to not have to worry about, is that an incentive that people like? Is that something that would actually change data as we know it? And this is kind of our proof of concept for this idea. So essentially Gravitino is our open source project, and it's now Apache incubating, and I'll talk about it a little bit more in a little bit, but we plugged in this metadata lake into a Llama index demo, and we kind of used it to be this basis for agents to pull in and out of. And it ended up working really well for us, where we had all of these different data stores, both structured and unstructured, and we have a lot of different connectors that we can offer. And so we then put this layer over top of it, and then we allowed machine learning systems to be able to pull from it and do what they did best, and it ended up working really well. So you can have baked in access control with this, you can have governance, and you can be able to see where it's going, which is great. So in turn, if you're going to have a metadata-driven architecture, it should really be end-to-end. A lot of what I talked about before with the tooling and the landscape, those will have their own, applications will generate their own metadata, but unless it's actually being looked at by somebody and being managed by somebody, which is a lot of burden anyways, it's not really going to be that useful. So you might as well just have another application do it, in my opinion. It should be. Cool. It should. This is the issue with universal remotes, by the way. Yeah. Yeah. And it should be vendor agnostic. So we're seeing a lot of catalogs now being open sourced, but not necessarily supporting the entire open ecosystem and providing the full functionality that it should. This is where our company differs in terms of Datastrato and what we're striving to do. This is a black screen that is now moving back to my PowerPoint slide. This is all staged, by the way. But are we good?
I don't know, I didn't hit anything.
Should I just turn my laptop around?
Maybe.
I feel like I've been too reliant on my slides, so maybe I should just wing the rest.
I mean, you might have to. You might have to. Well, I literally haven't done anything in this last year, and I'm like,
Have you tried controlling it with your mind?
try it.
I'm being recorded now, by the way. People on YouTube are definitely having a fun time.
Try to go to this one and not mess with that one.
Netflix on the screen and presentation on the screen? Yes, no? Yes? No? I mean, people can still see this one, right? Yeah. Okay, cool. Okay, cool. And so it should be vendor agnostic. And I think that in 2 to 3 years, we're going to see which data catalogs that are open source this week or next month are actually truly vendor agnostic. the truth is they probably aren't, and we're going to see that come to light a little bit. It's nice when something becomes initially open source and we get really excited about it, but then we see the differences in the features and the performance, and it becomes a really big issue down the line. And it should, of course, be trustworthy in your single source of truth as you have the single layer. And so maintaining it is actually really worth your time, because then you get to save time in so many other aspects of your organization. And so Gravitino, as I mentioned, is our company's open source project, now Apache incubating. And we refer to it as a metadata lake. This is a little bit different from a data catalog, because it's this pool for all of your metadata to come into, and then all your tools can kind of be in one place, but other tools can pull from it. And that's the really exciting part, is that it's just served as this basic REST API. We also have a Iceberg REST service as well. And so you actually don't need to migrate from anything to use it. You can just implement it right away, which is the really exciting part compared to, say, other metadata stores that you might see around. And so we have a very open approach. We have like one of the highest concentration of Apache members in our organization, which is really awesome. And we're really focused on simplifying architecture, even if it's really messy under the hood, so that you can enable like AI development right here and now and not have to worry about it. Now, that doesn't mean that you don't have to worry about like data quality or eventually migrating if you need to do that in your organization. But we kind of give you a bit of padding room to be able to do that, so that your source systems don't have to be like production ready right here and now. And so with this, you can actually unify efforts across different teams and have, again, different tools be able to pull off it, but essentially implement it directly into your pipeline in a way that enables RAG and in a way that is governed, which is super important, and in a way that is open source. And this is kind of under the hood of what we look at in terms of our architecture. So you can use a variety of execution engines. So you can use Spark, you can use Trino. We're also, hoping to add a lot more if anybody has one. StarRocks might be in the business as well. And then you can directly query through the APIs that we have available. And so how we handle this is that we have several, there's very many data formats, but whether it's tabular data, non-tabular data, whether it's a machine learning model, or say a Kafka messaging service, that all gets translated into a common schema, and then in the catalog, it shows up in the exact same way. So your meta lake is like somewhat standardized, and then you can choose your own metadata storage, or you can go through us. It's really up to you if you want to deploy it. Again, it's open source. And this is kind of just showing more of the same in terms of how we treat it. It really, once you're in the system, it's very agnostic, and you kind of see it the same way, but under the hood, it does get treated a little bit differently. And so yeah, we've gained quite a bit of traction over the past few months, especially in the past couple of weeks. So for instance, this is a breakdown of our number of commits and issues compared to Polaris catalog and Databricks Unity catalog. So for instance, we have 1,336 commits. Thanks, Jerry. Jerry, can you raise your hand, because a lot of that was him. And we also have 3,859 issues, which sounds like a lot of issues because it is, but that means that we're gaining a lot of traction on our project compared to 1 issue and 6 issues on the other repos that are available on GitHub, and the number of commits 2 and 2. So, Unity and Polaris tied neck and neck there. So if you want to trust open source, I think you should trust an active open source, if anything. And our lines of code are no joke as well. So 187,000, Jerry, can you raise your hand again? Thank you so much. So you can see that there's a difference between having a metadata layer that you trust and is being worked on actively, and the code doesn't lie. I know that I'm in a room of developers. And so yeah, if you're interested in our project, give us a star. We're used in production, and we're ready to be deployed at any time. Please feel free to scan the QR code. And yeah, I'm here to take any questions as well. Cool, thanks.
My name is Alice. I joined RisingWave actually 2 months ago. I learned a lot in this 2 months. I'm still learning. Well, I'm not the usual suspect to give a tech talk like this here today. I hope to share my experience working at Robinhood. That's where I first get to know stream processing, the power of it, and really got obsessed with the technology around stream processing. And then we'll go over some of the pain points I observed at Robinhood. I also testified from other companies that I talked to. And then I will go over, oh my God, I'm supposed to jump to the next slides. Sorry, bear with me. And then we will go over, give an overview of what RisingWave is two major innovations and how these innovations address the pain points in existing solutions in stream processing. And then lastly, we will go over how our open source community is really driving the development and growth of the project and the company. So back in 2021, I graduated from college and joined Robinhood as an engineer on the streaming platform team. During my time there, I got a lot of hand-on experience with stream processing, and I witnessed its transformative potential in handling real-time data. So I thought I'm going to give this talk to people who never heard of stream processing, but earlier I realized that we have a lot of data infra experts here. So raise your hands if you're already very familiar with stream processing. No? Okay, one person. Thank you. And then raise your hand if you heard of Robinhood. And then raise your hand if you placed a trade this week. Thank you, guys. Think about the last time you made a trade on Robinhood. Maybe you bought some shares of Apple or maybe GME. Maybe you sold your Bitcoin when it was at a peak. So from the moment you swipe up to confirm a trade, a message will be sent to some Kafka topic managed by Robinhood. And then there will be a number of serverless components in the back end which subscribe to this topic. And then maybe team A will validate this transaction, and maybe team B will update the user's portfolio, and then team C may record this trade in the ledger. A number of operations happen under the hood. And all these activities happen in mere seconds, and that's the power of stream processing. So in the simplest term, stream processing is about analyzing or acting upon real-time data, or we call events, and as they happen in real time. As opposed to traditional batch processing, you periodically scan the table, get some ideas of what's going on in the world, and then take some actions. And that's just like having a finger on the pulse of your business. You're constantly monitoring and reacting to changes as things happen. So here I have some common use cases of stream processing. You could spot fraud the moment it happens. Like you don't want to, like, you can't wait. You don't have a day or a week to wait. Because these things have a lot of consequences, and you can act upon user requests. As is my Robinhood example, people would have like a trading dashboard to show all the trade that's happening in real world, and that really help you make fast trading decisions. By the time you get a notification of something Elon Musk said on Twitter, and then act upon that, it's probably going to be too late. You want something that's like under 1 second latency. And I recently heard about this super interesting use case of detecting a bot as like a Yelp use case. So a lot of bots that people use to leave reviews about businesses, and that costs a lot of compute resource for Yelp's business. It also gives your user a bad taste about your service when they see a lot of reviews from bots. And we could also detect an anomaly that could signal a system outage. A lot of factories would have a bunch of sensors on their machines in their factories, and sometimes you want to be able to tell something bad that may happen in the next, I don't know, like minute, an hour, and immediately take actions to prevent and disruptive things from happening. And you could, the last one is a very common use case in e-commerce. You want to monitor the clicks about like your different products or services, and with that insight, you can deliver a personalized recommendation and some other offers to your user to improve the experience. So in general, stream processing is about proactively identify and resolve issues, take actions when events happen. So here, the diagram about some like real life application use cases based on latency requirements. On the very left of this diagram, you have under millisecond requirement, thinking about high frequency trading. For this use cases, you want to build your service as close to the trading center as possible and have like physical connections to achieve like under millisecond latency. And on the right hand, you have the very right end of this diagram, you have some machine learning training use cases. You have your data center, accounting. For these use cases, you really don't care about the latency. You can wait for days or weeks or even months to get the result as fine. And in the middle, you have the like scenarios where you want real time, like very low latency, like stock dashboarding that I just touched upon. Inventory tracking, that's another interesting use case. And as recommendations, that's one of the e-commerce use cases we just talked about. So we had Kafka at Robinhood, and it was really the backbone of the event-driven architecture at Robinhood. A lot of teams rely on Kafka to deliver real-time insights or taking actions upon users' requests. However, Kafka, while it's really good as a message queue, it helps you to move data around, it lacks some features for you to interact with real-time data streams in a more sophisticated way. For example, our team often struggles with implementing features that involve the time window. For example, you may want to aggregate how many trades you had in the last 15 minutes. It is possible with Kafka, but the implementation will be super cumbersome, hard to debug, very error-prone. Another pain point with Kafka is it's the bare metal Kafka consumers and producers lack the liability, scalability features. Half the team's on-call burden was on addressing Kafka consumers' malfunction. Like we get notified about some consumer got stuck, not making progress, or like zombie consumers, etc. Problem like that. And so soon enough, we realized that we had to add a dedicated stream processor to address this more sophisticated stream processing requirements. And after careful evaluation of available solutions in the market, we picked Flink, which is a very popular open source stream processor, open source stream processor. So while Flink is very powerful, it has all the capabilities that we wanted. Over time, we suffered our shares of the pain working with Flink. So the first one is the complexity barrier. Flink was built by the big data people. They had a very deep foundation in Java and Scala. So Flink, the programming model is based on DAX and Java, and it turns out like our data engineers who build data pipelines really hated that. They're comfortable with SQL and Python, but they really struggled with like debugging with Java, JVM, etc. And that caused like a lengthy development and testing cycle. So you had to like spare a week or two to just get familiar with Flink, and then you often have to learn about Kubernetes to deploy a Flink job. With Kubernetes, you have a Flink cluster, and then you look for logs and errors in the cluster. It was just a whole lot. And then we have fragile reliability issue. That comes with Flink architecture choice. Every time your job is done, you will have to load the state from S3 and then like rebuild that state within a Flink actor. That takes like anywhere between 5 minutes to 40 minutes, depending on how big your state is. There's also an operational burden because with Flink, you will have to pick how many compute nodes you want to use, how much memory resource you need, like all the system requirement, like this has to be configured manually. So people have to learn about like how much compute resource my job would need to make a reasonable, make up a reasonable numbers. And this high operational cost, you know, like so they're already struggling with learning about Flink. Now they have to like deal with this operational burden. So it just like caused a very long development cycle. There's another problem because it takes so much resource to redeploy a Flink job. There's a risk of a downtime, the fragile reliability there. People tend to we want to avoid restarting a Flink job. That the consequences, you often end up over provisioning your cluster to handle your peak workloads. We talked to people at Uber and Yelp, and we heard in their Flink job, the average utilization is about like 7%. You know, think about how much cost is wasted there. And so that was like in 2021 when I was there grappling with Flink operational burden. Yingjun, the founder of RisingWave, he also noticed his pain points with existing solutions, and he observed rising demands in stream processing. So he said, can we do better? Can we build something that addresses all the problems and give people the benefits of stream processing? And he made it. That's how he built RisingWave. He realized that a lot of this problem, this pain point that people been struggling with the existing solutions like Flink, is something that's rooted in a lot of decisions in the architecture. So it's not something that you could solve with adding another layer of abstraction. You know, as computer science, we often just solve a problem with like a new layer of abstraction, which oftentimes introduces new problems. So Yingjun, he came with a very simple idea. People want to interact with data streams, real-time data streams, the same way as they work with databases, with the language, with the interface they are most familiar with, which is SQL. So he built RisingWave with the fundamental idea is we want a stream processing capability, a stream processing system that uses SQL as the main interface. So I think over the years, many stream processing systems realized how much people want SQL, and they added SQL capabilities. For Flink, we had Flink SQL, and Spark also has Spark structure streaming SQL, something like that. However, those SQL languages are somewhat different from the SQL you use to interact with databases. As opposed to that, RisingWave, we fully commit to the ANSI SQL standard, and we build RisingWave to be 100% compatible with PostgreSQL. And like our mission is to just allow people to interact with real-time data streams the same way as they would with good old PostgreSDB. This really unlocks the power of like it's really democratized stream processing. And we heard from our customers that the moment they adopt RisingWave, their data engineers from like other teams all like started looking at the code, and they were able to contribute because they're like all familiar with SQL. There's nothing new to learn, and this really allowed them to get the most out of the data their business generates. So we're not. Oh yeah, here I put a few examples of how it works in practice. I hope like people can read this just like reading English. Yes, give me a thumb up. Yeah, so in this first example, we get like number of counts per product. In the second example, we are looking at like the temperature of devices, and like this is allows you to detect anomalies and take actions before something horribly wrong happens. And in the third example, we are like interacting with more than one data streams. We're performing a join to detect possible fraud scenario. Yeah, so RisingWave has been adopted by a number of industries. We have gaming, we have e-commerce, we have finance, we have IoT, edge devices, etc. RisingWave is not just about SQL capabilities. It is a lot more than just another stream processor with SQL capability. We're actually a full-fledged database. We are specialized in processing streaming data. Traditional stream processing engines primarily focus on computing, and they leave the storage aspect to the user to deal with. They might offer some very basic state management capabilities, but they don't provide the same consistency and query capabilities that you would expect from a database. So with RisingWave, you get the best from both worlds. It handles the continuous flow of data like a stream processor, but it also provides the data management and query capabilities of a database. Because it has knowledge about your data, about the storage, it is capable of like optimizing your query in the fly. So this way, the performance of the queries could be a lot faster. I had one slide here that illustrates what would happen. Like, without any query optimization, you have the diagram on the left. But when you understand how data is distributed, how data is stored in your database, you will be able to like change your join order and achieve the best query result, query performance. Also, because you have like a storage layer, you're able to have an intermediate result, store your intermediate result within RisingWave, and then like do some further computation on top of it. So here is another big pain point from Flink. Since it doesn't store the data within Flink, you never know what's going on. It is a black box. So you will have to sync the compute result into another data system, usually is Kafka, and then you have to set up another Flink job that's subscribed to this intermediate Kafka topics to do your follow-up computation, and then sync it like to another Kafka topic. It goes on and on and on, like many hops. So one of the consequences is additional Kafka management cost. Kafka is a complete beast. The operation, like it adds to your cloud bill. We've heard about this from people at many companies. But in comparison with RisingWave, you could have everything happens just within RisingWave. You can store the intermediate result as a materialized view, and then do your follow-up computations on top of it. You can have as many materialized views as you want. We had customers that had like 2,000 of materialized views, and it works very well for them. And then constantly we get people to talk to us and give us these messages, which really makes us happy, because we addressed a real problem people struggle with in their business. So they really get it. And so far we covered the first major innovation of RisingWave, which is the streaming database aspect. I remember I talked about like one of the, like there's another aspect in Flink, except the learning cost, the learning curve, and the complexity of Flink. Another thing is about reliability. It's about elasticity. People tend to provision their Flink clusters, and they require you to manually configure the compute resources. We realized that we have to address the elasticity problem. We have to give people a reliable experience in running their stream processing jobs. And our answer is a major architecture decision, which is decoupled compute and storage for state management. So here's a illustration of the comparison. So in Flink, your compute node stores its state within itself. And in RisingWave, compute nodes are stateless. You can always add new compute nodes to the cluster, and we will be able to access state, which will be stored in persistent storage. You will be able to retrieve the current state and then join the compute. I thought about analogy of this comparison. So imagine you run a restaurant that has a kitchen of 10 chefs and 10 cooktops. So with Flink, the chefs and the cooktops are integrated together. When you have increased demand on for dinner, you have to add more cooktops and add more chefs. You have to interrupt the current operation. You have to plug in the cooktop that the new chef brings in, and then everyone has to stop, wait for the integration to finish to resume the work. And with RisingWave, you imagine you're having a kitchen that has unlimited number of cooktops. And then when you have a rising demand, you have more 10x your customers coming in for dinner, placing the orders, you can just add another 10 or 20, 50 chefs in, and they always have cooktops available for them. You don't have to interrupt existing operations in the kitchen. So this way, this architecture decision brings up a lot of benefits. Elasticity is one of these. Another thing is when you have an upgrade, when you want to change some configurations, you want to change your query, etc. The downtime, there will be slight downtime, but it will be in the order of seconds, as opposed to Flink. When you have a big state, the downtime could be up to 40 minutes to or even longer. Yeah. So this is a data infra, open source data infra event. RisingWave has been open sourced back in 2022. We currently have 6,500 GitHub stars. We have over 150 code contributors. For reference, we have under 40 developers in the company. So over 100 contributors there are from the community. We have over 1,800 Slack members. I checked this morning, we have 1,846 Slack members. By the way, I encourage you guys to join our Slack space. I assure you, you will be impressed by the passion of our community. And we have over 150,000 Kubernetes deployments. And recently, our director of marketing shared with us that we got over 8,000 LinkedIn followers, and we have a little over 2,000 Twitter followers. And we have this diagram of start history. We're comparing RisingWave start history with Confluent, KSQL, and Materialize. So the red line is RisingWave. We're very proud. We're very glad that our solution really addresses a problem for people and they enjoy using our product. Yeah, so that's it for my talk. Thank you all. And here I put a QR code for you to try our product if you have some real-time data processing needs. If you're here supporting the first talk I ever gave in public for my company, I'll offer you a $100 credit. Just email me.